All right, so today, I think I was told there is a clicker here. Here we go. I would love to talk about the challenges we faced, serving LLMs at scale at Union, and how maybe you can do the same. And to kick things off, I'd like to share a story that happened, not so long ago. It's a bit personal, so my wife likes to change furniture every so often when we can afford it. So we were, on a shopping trip for a coffee table the other day. We found a great table, but with a very shocking sticker price. And I had one of those moments where I looked at the table and I thought, how hard can it be for me to just build it? And it started a journey, few months, and hundreds of dollars spent, and ended up with something that wasn't quite, that didn't live up to the expectations, I would say. And we ended up going back and buying the table anyway. Tell you this because in working with a lot of the companies out there using our open source software, there are thousands of them, and over the past 7 or 8 years, we work with a lot of them deploying and helping them run ML and AI systems in the company, on the company infrastructures. And we see this very often. Companies start at this journey at different stages. They either start with, we will build everything ourselves, and then it keeps evolving. They keep bolting on more and more features, and then they end up with a system that's not quite maintainable before realizing that maybe there's a that can do the job for me much better. And then other companies, take this the opposite approach. We'll start on day one. Let me do the research. Let me do the fact finding. Let's find a system that does what all the requirements we want to do. I want a system that's reliable, has the durability, the observability, the cost controls, all the governance that I want to instill in the company, and then go find that system, use it, and those teams usually get far further, faster, and are much happier as an outcome. One of the, as it pertains to today's topic, one of the problems that we see very often people start with is this sort of illusion of how easy things can be. Because you can run a model today on your laptop. You can open up your laptop, download Llama CPP or Ollama, and in a couple of minutes, you will have a model running that can start answering your prompts very quickly. And you can think, well, how hard can it really be taking that thing I just did and push it to a production system and let other people in the company start using it. And it is hard. One of the, some of the things you will run into very quickly is you will notice that the containers are very slow to start up. I was talking with a few people outside yesterday and today, and we are hearing 10 minutes startup time, right? So just to get a machine up with my model to start serving requests take 10 minutes, and this kills any real life use case. And then you start getting these unpredictable performance as more people start using the same machine and the same model as the conversations get longer and so on. And you find yourself, instead of focusing on the business logic of what you're trying to do, you are spending all the time really optimizing infrastructure and working around scale issues. And it's not quite what the company is probably paying you to do. We'll get back to this slide later on, but it's just here to tell you the grass can really be greener on the other side. There is an upside, and you can get results that are much more workable than the status quo today. What I would like to do for the remainder of the presentation is do sort of a build out. So let's start with a simple model, and we'll take that, we'll start adding more pieces to it. And that's what we ended up doing, and I'm trying to share what you can do on your own to also get there. Right? So all the pieces that you need to put together to get to a point where a model can really be served on your stack, in your infrastructure, and achieve the same low latency that you would get or is promised from these sort of API providers out there. So let's say you start with that sort of naive solution. You grab a machine from EC2 or from Google cloud infrastructure, and you throw in a container on it, a VLLM, and then you point it to a Hugging Face to download a model to serve Llama 3, for example, or Llama 4 now. You will notice that bringing up this container takes time because the container is about 15 gigabytes, or if you're using latest NVIDIA Dynamo containers, it could be 30 or more gigabytes. Downloading them takes maybe a couple of minutes. Then loading the model itself, which happens all the way after the container starts. These models can be 100 or so gigabytes, would take a couple more minutes, right? So you already shot any sort of expectations. You lost the user who was trying to run a query or expecting results from this machine. What can you do? Let's talk about these two problems individually. Let's take first the container startup time. The conventional wisdom, I guess, is you need the container, right, to run the code, run the binaries inside that container. There's a lot of research that was done, not by us, by other people, that show the most containers out there don't really need all the files in them. So in average, it's about 70% of the files deleted from a container. You are still fine. You can still run the container just fine. And that is because all the dependencies that are put in there, the libraries that get pulled inadvertently, and all the other things that in the container just in case to support other use cases, right? In the case of VLM, there are a lot of optimizations for all kinds of models, but you're starting it for a single model. You don't need all the other stuff. To address that, there are a couple of open source projects out there, something called Nidus, there's StarGZ, and you can roll your own. The basic idea, the basic premise for these projects is you can run a container once, you can record all the file system operations, so you can tell which files are actually needed for that container to start up and start putting the model. And then you stop the container, you reshuffle the layers of the Docker container so that it downloads these files first. And those will be in megabytes, not in gigabytes, right? When you get those, and you start the container immediately. And you can reconfigure the runtime to do that. So you get the container, quickly start, and then for model download, instead of pulling it from Hugging Face over a single HTTP connection that's limited in bandwidth and how much parallelism it can get, you can cache this model into an object store where you can get much higher bandwidth to download. And the goal here is to saturate the network, right? This is getting the optimal startup time will depend on how fast you can pull bytes through the network to this machine. So you can write a piece of code, which is what we did, to stream the models instead of the out-of-the-box experience you get, which again over a single connection downloads the model to the hard disk, then load it from the hard disk to the GPU. You can skip these hops by streaming a lot of connections in parallel, and then streaming them directly to the GPU, bypassing this extra hop of storing and reading again. If you get there, and it's not, maybe I'm skipping through a lot of the details, but if you get there, you are already 50–60% of the way to your optimal speed, sort of speed of light, because you're already running at capacity or at the highest utilization you can get from the machine and from the network. Then as soon as you start talking to this model, you will notice that as you talk more and more, your conversation is getting slower and slower. As the sort of context window or your previous prompts are getting sent over and over again to the model, it's getting slower over time. But to understand this, I'll have to dig in a little bit in the details of what does the model do with this big prompt that keeps getting longer and longer every time to make it slower. There's something called KVs. You probably heard of what that is. Basically, for every token in the input, it needs to compute a bunch of matrices and they never change, right? As soon as because the prompt, you only add more and more to the prompt. You never go back and change, the previous tokens in a prompt. So those matrices don't change. But because it doesn't know about them, it doesn't know that it has seen this prompt before, it will recompute them every time you send a prompt and you add a word or you add another follow-up question to it. It will recompute them over and over again. And if you did any computer science classes, the easiest solution for something that keeps the same results happening over and over again is you throw in a cache in front of it. And that's what you do. VLLM also comes with an implementation of a cache. It's local. It caches. It has like a multi-tier thing. It will cache in the GPU memory first, then to the main memory, to disk, so that if it has seen the token before, it has seen that sequence before, it will just look up these matrices and not have to redo them again. It's great. And we're getting to, as problems, I think, as we progress with building out the system, the problems become more and more designing distributed systems problems than an LLM problem. Right? The model hasn't changed. The tuning of a model hasn't changed, but all the pieces around it matter a lot more to get this performance out of it. And then you will notice that as the performance is great now, right? Every prompt is about the same latency as previous ones, even as it gets longer. But you consistently see these time to first token still slow, right? The first word that gets sent to you still takes time, and usually unpredictably, sometimes it would take longer than others. The reason for this is something, is a sort of, maybe a limitation in how the model responds or generates responses to your prompts. It does it on technically 2 stages, but because we are forcing the model to run on a GPU, it's forced to use that one GPU for both of these stages. There's stage, a prefill and a decode stage. In the prefill stage, it's a lot more compute intensive, where it's doing a lot of the GPU, the matrices multiplication for computing KVs for the tokens that were not computed before. Once that is done, the decode step is a lot more memory heavy, with looking up. Most of the work here will be looking up existing KV tokens and a little bit of still matrix multiplications to generate new tokens. But because we're putting them on a single GPU, it's limiting the throughput of that single GPU, what it can do. So the simple solution is to split it, right? Reserve two GPUs instead of a single GPU, right? We're adding more cost here. For smaller models, you can actually partition the single GPU. NVIDIA has an operator that lets you make a GPU look like 2 GPUs. If you can split the memory, if the model fits in half the memory, so you can reuse the same GPU, appear like 2 GPUs, and split these stages on 2 GPUs. Right? Of course, this thing can scale to more. If you can put 8 GPUs on a machine, they can be 16 GPUs, and you can load the model, right? 8 times for each stage. They don't have to split it, down in the middle. Depending on the use case, you may want more GPUs doing prefill than decode, and the whole thing we can talk about later on. But in the simple case, you end up with something like this, right? You have your host, you have 2 GPUs running there, you have the KV cache, and you have a little like router that, sort of orchestrator, right? It does the pre-fill, takes the output, pass it to the decoder, and then gets back your results. And you like this, you replicate it, right? You just add a horizontal autoscaler on top. So, as people start using the model more and more, you just boot up more and more of these machines, either on the same machine or on other machines, and you hit the next problem. Because there is no way to know which machine will produce the faster responses, your system is probably just round robin, or like sending them to random machines. And then sometimes you will get fast responses when the cache is there, sometimes you don't. And it requires you to add a couple more components in front, right? So now you need a smarter router on top that's more than our typical services routers. You need something that understands that the queries coming here are LLM queries, so that it can look up its own cache. It can look up an index tree to know that, oh, this query has seen before coming from this machine. So let me send you there. You're more likely to get faster response from that machine because it knows about the KVs from this query. Or even if it's a new query, it can still find the machine with the maximum sort of cached tokens, right? It can know that maybe half the tokens are known by this machine, so let me send you there. And these are all new concepts that don't really exist for today's, like if you're just building a fast API apps or any like typical API service-based APIs. Everybody's happy in the company, right? The models are getting popular, more usage is coming, and then you want to go global, right? You want to run this at different regions. Maybe you want to get cheaper GPUs. A lot of GPU providers out there that offer a lot more sort of competitive prices than the hyperscalers. So you just want to make this available elsewhere. And this requires a much more complex router than, again, your sort of typical thing you get, run-of-the-mill router you get from Cloudflare or from AWS or GCP, because you need something, again, that understands these are LLM queries or queries for large language models, and they need to understand that just because you are close to a cluster or to a server, it doesn't mean that that server will send you the fastest response. It might be better to send you somewhere else where the entire query was seen before, because then the response will be a lot faster. Typical routers just are based on sort of ping latency, right? They try to send you to the closest machine to your geographical location, because these services are stateless, and the expectation is, the closer you are, the faster they will respond to you. Again, we skipped over a lot of technical details. I'm happy to dive deeper if there is interest in any particular area. We have a booth outside, and the team have, I think, 4 or 5 of us out there, and we'll be happy to dig in any of these topics with you. So you get there. What you end up with is much better performance that we're not quite happy with it yet. I think there's a lot more improvement that we can do, but you get to a point where instead of spending 5 minutes or 10 minutes booting up a machine, you can get to a working 70 billion parameter model in less than a minute. It's a huge improvement. Our goal is to get this down to within a request timeout, so like less than 30 seconds, and get you off the ground. So even that first request that tries to wake up the machine doesn't time out, and I think we'll get there. Let me zoom out for a second, tell you what else we do. So Union, we started the company, as Nadia shared, a few years ago, with the goal of building the entire AI development platform. We started with an open source project that we built a few years earlier at Lyft called Flight. It's an Apache 2 open source project. Please check it out and let us know. We can help you use it. Flight is focused on the AI workflow orchestration problem. It's Kubernetes native, and it runs anywhere where you can run Kubernetes. And at Union, we are trying to build all the other pieces in this puzzle so that you can get one-stop shop. You can get this one or a single pane of glass to develop AI models, you develop workflows, all the pieces you need for your AI needs, getting to agents with all the production requirements, the durability, all the retries you need, the observability, the cost controls, the logs and the metrics, and all of this in this one thing that is privacy conscious. It runs on your cloud. It runs in your infrastructure, and it's very compliant with all the governance needs you may have. The piece we were talking about today is this highlighted in red, the real-time inferencing. But the infrastructure is shared to use for batch inference, super fast batch inference, for more complex workflows where you want to run production grade inference or training, fine-tuning your models, and all with the observability as sort of the layer at the bottom common across. Let me leave you with this. And we will end a few minutes early to open it up for questions. I think we got to a point where there are a lot of these models coming out every other week. And I think even more of them will come out as months and years come. And I think more and more companies will be moving in the direction of serving their own models, serving their own LLMs for various reasons, whether it's regulations or cost control, or in some cases, even performance. And I think the key to success of these attempts or these deployments is thinking about the system, the entire system that needs to be built around them, not just about optimizations done at the model layer or the model stage. And I think it's time for us, all of us, to really work together on building this system and best practices, patterns that can enable everybody to ship their own models or benefit from running their own models. So we'll be outside, be happy to talk with anyone who's interested to collaborate. We have a very vibrant open source community, and would love to see you all there. And thank you.
So in the first or second slide, you mentioned the Docker file, you can have lower megabyte files in the beginning so that your container can actually start. But my question is, why? Like, you still need to get the model in to actually do the inference. So what is the point of starting the container if it's not ready to serve the requests because the model isn't there in the GPU yet?
Great question. So there are two ways people ship models, right? You either embed the model in the container, or the model lives somewhere else that you pull over the network, right? The model I was talking about is when you have a container, like a VLLM container is about 15 gigabytes with no models in it, right? So it starts up and then pulls the model over the network, right? So you want to get to a point where the code inside that container is up and is able to start the network request to pull the model as soon as possible. If you wait for all the 15 gigabytes to be downloaded to start up, you already wasted a couple of minutes, right? Before you even pull the model in. Right? It's like you think of it as a timeline. You spend 2 minutes downloading the container, then 2 minutes downloading the model, right? You want to shorten both of these periods to get the overall time shrunk, right? So that first part gets you that first period shrunk to seconds because it gets to the script that will make the network request to start downloading the model very quickly in the first couple of seconds of starting the container. Does that make sense?
Got it. Yeah. Thanks.
Yeah.
Thank you. Thank you. Okay, so the fascinating talk. Thank you. And I love the fact that this room has this kind of theme, because this is very timely, the topic here of your talk. So basically, it was implied in what you were saying, getting just LM out of the box versus deploy your own. It was very much the latter was implied in your entire talk. I suspect you've done multiple cost analyses, and the pricing keeps changing. New tech comes in kind of every other week, well, every other day, honestly. Can you give me some insight regarding that cost analysis? So some of these out-of-the-box LLMs, as APIs, LLMs as service, are becoming really cheap with Gemini, kind of really affordable, versus in-house deployment, right? So my gut feeling tells me that definitely in-house you can have a lot of advantages, but I suspect you've done a thorough cost analysis. Could you give me some insights? Thank you.
Thank you. That's a great question. I don't have numbers on top of my head to share, but because the numbers keep changing, as you pointed out, the pricing keep changing. The pricing for the GPUs keep changing. But I think that it will always be these sort of two graphs that will intersect at some point. As your usage of these APIs increase, your pricing, or the cost you're paying, will increase drastically, quickly. And then on the other side, your utilization is really the metric you want to look at when you're talking about self-deployed models. If you get utilization high enough, the cost benefits will always play in your favor. If you have very low utilization, it's almost always a better idea to go call the API, right? Because you are not going to benefit from a GPU coming from whatever cloud it is, right, at very low utilization. I think it's on.
Thank you for that. Specifically, I was actually looking for the latter, the very high utilization with reasoning models and already agents. So that means these are going to be very, very chatty. So that's what I'm looking.
I think if you guarantee a high utilization, it's almost guaranteed that it's better for you to deploy your model. I think the other factor you should consider is there is a race between how smart these open weight models are and how Gemini and OpenAI are investing in their models. And that will continue forever, probably. So if you find a use case where the open weight models are good enough for you to use, it will, I think this will work. Yeah, makes sense. Cool.
Cool. Maybe another last question, and then we are going to close.
Okay, Jeremy.
Hello, I'm a big Flight and Union fan, thank you. My question was, other companies that preload, instead of loading on the fly when the customer requests, it just kind of predicts when there's going to be a bigger load and it just preloads a bunch of GPUs with the data so it doesn't have to wait as long. Is that a practice that people do?
Yes, that is a practice people do. So there is a whole topic about capacity planning between picking the right size of machines, the right GPUs, the right memory requirements for your model and use case and all of this, and also how many of them and when do you get them. And this is maybe we can do another talk about just the capacity planning. But yes, you are absolutely right. You can tell by prior days that nobody used the machines at 12 a.m. and onwards, so you just turn them off, or vice versa. I don't think it doesn't negate the need for the scale up, for the cold start, solving cold start problems, I think, because you will always have these bursts, unpredicted load that happen. And even when those happen, you want to be able to scale up really quickly in response to your, the increased requests. So I think it maybe is a requirement, a prerequisite, but both of them need to exist. I agree.